Hey Panthers! This is lesson 1 of your topic in your remote learning book, Expressions and Equations. So make sure that you've got your remote learning book and a pen or pencil in front of you and you're ready to follow along in this lesson.
So let's dive right into the lesson on topic 3 in algebraic expression. So if you don't have your remote learning book right in front of you, you might want to go ahead and grab that and follow along for our guided lesson. Now, the first page of your ready lesson looks like this, and it is a review page. But the thing about the review pages is that these are lessons from your iReady book, and the review lesson that they're referring to, we didn't do, or we don't have that available in our remote learning books. So on the slide prior to this, I have a video that is all about writing and evaluating expressions. This is a video from Anytime Math, and they do a great job of explaining how to write expressions using the words. So they basically go through a bunch of examples of where you see the words and they pick it out and learn how to write an expression. This screenshot right here is from that video. It's a phenomenal resource of just making sure that you've got that foundational knowledge that you need to be successful during this unit, this 2 weeks of expressions and equations. I also have some more resources listed at the bottom, including the Khan Academy video. This is only a 3-minute long video, but it includes all the lessons like Khan Academy does a great job of doing. So you start by watching the video, and then they have practice problems for you. And after you master the basics, it moves you on, gives you another video and teaches you how to do it a little bit harder, and then gives you more practices, and it continues on. So the Khan Academy is a great resource here to be using for that refresher. And then I also included the BrainPop video, which is 5 minutes, just to quickly review over about this writing and evaluating expressions. So as we move on to our first page of our actual lesson, we're going to be describing this expression, 2x plus 5, in our own words. So when we see the expression 2x plus 5, and what makes it an expression is that we've got this variable or letter in it. A is just strictly asking us, what does this letter even stand for? What does x stand for? In this case, we don't have any sort of story that goes along with this problem. We have no context, but x is always, in every story problem, it's an unknown number. And the reason why we use variables is so that we can plug in many different numbers or values into this x, and we can get the answer for, if x equals 1, 2, 3, 4, we can get multiple answers by plugging in numbers. We're very quickly reviewing when we see a number side by side with a variable or a letter. So we see number and letter, and we have no operation in between. So there's no parentheses, there are no multiplication or division signs or addition. So how do we know what operation is happening here? So whenever you see a letter and a number side by side with no operation, it is being multiplied. So this operation is multiplication, if I could spell it. That's something that I really hope that you remember from in class, like when we were back at Loris time. Whenever you see that number and letter next to each other, it's multiplication. It is absolutely crucial that you remember that, because you're going to be having to come up with your own equations. So you need to be able to write down 2x and know that you're being multiplied. And what do you call the result of this operation? So when we multiply two numbers, the answer is called a product. And again, this is another piece of absolutely crucial information that you must know, because if you don't know that a product is the answer to a multiplication problem when they're going to be asking us to come up with these equations using your own words, or I'm sorry, using their words, and they say the product of these two numbers, and you don't know that a product is multiplication, you will not know what operation to do. So the answer to a multiplication problem is a product. The sum is going to be the answer to an addition problem. A difference is the answer to a subtraction problem. And a quotient is going to be the answer to a division problem. So this information, and it was very well stated in the video that I gave you, and those words are included on that original chart, but these are going to be the answers, and this is an extremely important little graphic that you must know. And then it says, what operation does a plus sign show? I hope that you all remember, I know it's been a while since we've been in school, but a plus sign is addition. And what do you call the result of this operation? If I look over here, the addition problem, the answer is a sum. When I add two numbers together, that answer is called a sum. And then F says, explain what the whole expression represents. So I need to go back up. It says 2x plus 5. So this whole expression is really representing these two numbers being added together. So we're going to write down that the expression, represents, remember I'm always trying to use the words that our author is using, so when I'm rewriting my question in a full sentence, I'm using that same verbiage. That's very helpful on your MSTEP and your NWEA test, is using the same verbiage that the test is using. So just keep that in mind as we write incomplete sentences. So the expression represents the sum, which is the answer to an addition problem, of the two amounts. And then the first amount, so if we go back up, the first amount is going to be the product, or the answer to a multiplication problem, of 2 and the unknown number. So let's write that down. So the first amount is the product. See, I'm using this math vocab. It's absolutely important that you guys are not just saying the first amount is the answer of the multiplication problem. Use that verbiage that you know. It's going to help you so much in the long run. Just by even remembering, if I continuously write that the answer to a multiplication problem is a product, then in my head it is never a question of what the answer to a multiplication problem is. So the first amount is the product of 2, the number 2, and an unknown number, which is x, which is a variable. And then the second amount is just 5. And so if I were to take this explanation and give it to you, you should be able to come up with this equation. So when I'm looking at just my explanation, so if in the future, if I ever have to write an explanation to showing what an expression represents, I should always, to check my answer, I should be able to read this all by itself and come up with that absolutely same equation. So if the expression represents the sum of two amounts, so I know there's an addition, and I know my first amount is 2, and a product would be multiplication, so 2x, and then my second amount is 5. So absolutely, that's a great explanation. If somebody were reading that, they would be able to write the corresponding equation, which is the goal. So down here for explaining what the whole expression represents, I could say we added two numbers together, and that was it. But if that was my explanation, I wouldn't be able to come up with this equation, which is the goal. So this review sheet, this review right here is super important. And if you're still struggling a little bit here with, understanding how to come up with this explanation and, using this equation, we're going to be doing the opposite now. So we're going to be reading a lot of explanations and coming up with our equations. So if you're still struggling a lot with that foundational knowledge, make sure you go back to that previous slide, check out some of those videos, and give yourself a nice base knowledge before you move in to the entire unit on expressions and equations. This slide right here, slide number 4 or page number 99 in your book, is extremely important. Important enough that I am going to highlight it. This is kind of like your notes. They're basically giving you notes that you can come back to and refer to when you're working on that independent work or if you're working on any other assignments. And I'm just going to quickly go over this. It says you have evaluated expressions with known numbers and operation signs. An example of this would be 6 minus 7 times 4. So we've already done that. We can do that. You guys would know to multiply 7 times 4 first and then do 6 minus the product of 7 times 4, order of operations. But now we're going to include those variables. And a variable is a letter that stands for an unknown number. Very important. I'm going to underline all of these important definitions. And then we're going to look at this expression, which we actually just kind of dug deep into, this 2x plus 5. And as we start to define the words, I'm going to go back and refer to what we came up with here and how our vocab can relate to our diagram. So a variable is a letter. And so we know, I don't really want to go that far in. Okay, whatever. We know that this x right here is a variable because whenever I see any type of letter in a math problem, I can call that a variable. And then the next thing that it says every expression is made up of terms. A term is a known number, a variable, or the product of a known number and variable. The expression 2x plus 5 has 2 terms. So let's hold up and talk about terms very quickly. So terms are going to be a known number, so just a number by itself, like this 5 right here, that's a term. It's a known number. By itself, done. Term. Or the other way that we can express what a term is the product of a known number, like this 2, and a variable, which is our x. So we can see that based on the definition of what a term is, we've got this term right here, which is just a known number, and we've got the second term over here, which is the product, which is the answer to a multiplication problem, of a known number, which is 2, and the variable x. So this problem right here has 2 terms, or I'm sorry, this equation or expression right here has 2 terms. The next thing that we are going to talk about is constants. And it says a term that is a known number without variables is called a constant. So a known number, meaning it is a number, it doesn't have any letters attached to it. So we can see that this 5 right here is a constant because it's a known number. The 2x is not a constant because we have a letter attached to it. So the constant is 5 in this expression. And then the next part, the next definition that we're going to talk about, the next term, is a variable term. So we know that a term is going to be either one of these numbers, a known number or a known number and a variable. But the variable term is the term that has the variable. So if any term has a letter, which is called a variable, that's considered a variable term. If this was 2x plus 5y, it would be 2 different variable terms. And then it's more specifically diving a little bit deeper into that variable term. And then it says if one factor of those numbers that variable term, so looking just at 2x, if one of those numbers is a known number, this number is called the coefficient. So this is my variable term, and I know it's my variable term because it has a letter attached to it. So if I look at my variable term, the number that's attached with it is also called the coefficient. And then these terms we are going to hear a lot about over the course of the next couple of weeks. So keeping this known and highlighting it, or, putting a sticky or, folding over that page number just so this page is very easy to come back to. I think that would be very beneficial in the long run when talking about expressions and equations. So the last thing, it says, look again at the term 2x. Remember, whenever we have a number next to a letter, it means to multiply an unknown number by 2. So we usually use that x for the multiplication symbol, but when we're using, so this is basically them just showing the different ways of why they do that. Like, why don't they just write 2 times x? And the reason being is that x is one of the most common variables that is used in math. So it's the most common letter. X and y we see a lot through our books. So we also use that x for multiplication. So if we look right here where it says the expression 2 times x would look confusing because we have like the times symbol and then we also have the variable x. So sometimes we see it written, and you guys have seen me write this multiple times, where instead of writing an x, I draw that little dot, and that also means multiplication. Or you could just write it as 2 next to x, and this also shows that it's being multiplied. So now that we've really gone into depth about our vocab and what we're going to be doing, let's take a look at this first reflection. Claire says the expression 8x to the third power, or 8x cubed, has 3 terms because she's got 8, x, and 3. Is she right? Based on her definition of a term, I'm going to go back and look at it. It says that a term is a known number, a variable, or the product of a known number and a variable. So when I'm looking at just 8x to the third power, I can say Claire is, oops, I spelled her name wrong, is incorrect. And the reason being is that a term is a known number, a variable. Notice how I'm going back and using the author's same words. A term is a known number, a variable, or the product of a known number and a variable. So x8, and I can't draw that little baby 3 unless I really go and do a whole bunch. So I usually write it with a caret is what we call it. It's like, it looks like a little carrot head. And when you see, whenever you see something that looks like this, with like a carrot head and then a number, I'll try not to use that very often, but in this case, I really don't have an option. That carrot head 3 means that it's raised to the third power. So I want you, whenever you see a carrot head 3, I want you to think of it looking like if you were to look up into this description, how it has the small 3 up there. So we have 8x to the third power is, whenever we see 8 to the third power, we know that we're multiplying, x to the third power. We're multiplying x 3 times. So I could rewrite this problem 8x to the third power as 8 times, see, I don't really want to use my times because I don't want to confuse you guys. So we're going to do 8, and I'm going to use, this little thing is going to mean times for me for right now. So 8 times x times x times x. So if I were to rewrite 8x to the third power, I could rewrite it as 8 times x times x times x. And when I'm looking at my definition of a term, It says, or the product of a known number and a variable. A product is multiplication. So here's my known number, and these are I'm just multiplying my variables. So, therefore, 8x to the third power is only one term because it's a product of a known number and a variable. You can't just take each individual number or letter and think of that as a term. You've got to think of the grouping that they're doing. So 8x to the third power is, in fact, only one term, not three. Moving on. All right, we are finally into our instruction time. So, reading the problem below, we're going to explore ways to write the expression just by using the words. So this says, write an expression with the same meaning as subtract a number times 4 from 10. And so whenever we are looking at the operation words, I always like to kind of split it up into each individual term. So they're asking me to do one thing, and I'm going to figure out what that term is, and then what operation goes in between, and then what my following term is. So looking here, it says subtract a number times 4 from 10. So the first thing that I can think of is I see that word subtract. So I am going to put a subtraction symbol down on my paper. And then now I'm trying to think of what are my two terms that I'm looking for. So I know it's going to be a difference, and this is going to be kind of what the overall shape is going to look like. I know there's going to be a term here, then there's going to be a subtraction sign, and I know there's going to be a second term. Setting up the shape of the expression, it may seem like a little bit of wasted work, but it really makes it easier when you're trying to figure out what numbers am I looking for. It makes it easier to kind of hone that in and say, oh, the number times 4 is this term, so I'll put that there. It really makes it easier. So writing this down is pretty important. So this is the first step. The second step was thinking of expressions to help you, similar expressions to help you write it. So this first expression, it says write an expression for subtract 6 from 10. What is so important when we're talking, especially it seems to be like in subtraction problems, we know that whenever we're subtracting how important the order is. But when we're reading problems, it's especially important to focus in on what the order is. And I know that they go into that in that video that I linked in the beginning. So when I'm looking at writing an expression for subtract 6 from 10, my first term is going to be 10 because I know that I'm subtracting 6 from 10. When I see that word from, that's a very big key word that this is going to be my first term. So the way that we could write this expression of subtract 6 from 10 would be writing it as 10 minus 6. And then if we move on to thinking a little bit more abstractly, it says write an expression for subtract a number from 10. So now we got rid of our number 6, and we are just going to replace it because we don't have a second term to write. We don't have a number to write. So we are replacing that verbiage of a number. We're going to replace that with the letter X. But we're still subtracting from 10. So 10 is my first number, and I'm subtracting a number, which is an unknown, so I don't know, I can't write anything. So I have to use a variable. And that's why I do 10 minus X. And then it's asking us to write an expression for a number times 4. Again, I don't know what this number is, so I have to replace it with a variable X. So whenever they're asking you for a number, that's when you're going to be using a variable. When you don't know what the number is, that's when you use the letter. So if I was writing an expression for a number times 4, I could write that as 4x, because that's 4 times x, remember? Or 4 with the dot in the middle, x. So this was just a way that you need to start thinking. It's an example of how your brain needs to think when you see a problem like this. So let's move on to the connecting it. And this one, you might have to be really looking into your remote learning book and using both pages, because I can't show both pages at the same time. So it says, look at the first model it on the previous page. When you subtract a number from 10, will 10 be the first term or the second term? Explain. So as we kind of already got into, it's 1000% going to be the first term, because I'm subtracting from it, which you really have to pay attention to what you're reading. So that's going to be the first term, that 10, because it says I'm subtracting a number from 10, meaning I had 10 to begin with, and I'm taking some away from that. And it says, Erica says that the expression 4x has one term. Is she correct? Absolutely, she is correct. Yes, because 4x is the product of a known variable, or I'm sorry, a known number and a variable. And if I go back and look at my definition of term, that is exactly one of the options of a term. And if you want to get a little bit more specific into number 3, we can say that not only is 4x a term, but it's a variable term, because it has a variable in it. And then number 4 says, looking at the second modelet, so thinking of the similar expressions, and it says, write an expression for subtract a number times 4 from 10. So again, I'm thinking of my first number. I'm subtracting. How I think of it in my brain is my first thing that I try to figure out is what's my operation. And in this case, they straight up told me it's subtraction. But in many cases, it's going to say find the difference. And you need to know that that's subtraction. So my first step, at least the way that I do it, is trying to find out what is the operation. And I know that it's subtraction. So I try to put down my minus sign as soon as I can figure that out, just so I don't have to think about it anymore. And now I'm trying to think of what are my terms here. So subtract a number times 4 from 10. We kind of already figured this out. We know that 10 is going to be my first number because I'm subtracting from it. But now, what am I subtracting from it? A number times 4. Well, we know that a number, whenever we see the word a number, we should be thinking about a variable, because it means that they're not giving us a number. A number times 4. So we're going to write this as 10 minus 4x. I came up with my operation, my first term, and my second term. And then number 5 says, list each term in your answer to problem 4. So this case, there are 2 different terms here. The first term is 10. And 10 is a term all by itself, because the definition of term tells us that it is a known number. So 10 is a number that I know. It's a term. It's all by itself on that side of the subtraction sign. The other term I have is 4x. And that's a term because, like I said in number 3, it's the product of a known number and a variable, so it's a term in its own. And it says, does your answer to problem 4 have any constants? And while you look at 10 minus 4x and you think of the example in the book, they said that a constant was a known number without variables. And in the book, that constant, it was 2x plus 5, so the constant was the second term. I'm looking at number 4 and I have 10 minus 4x, and I have that supposed constant as my first term. Does that mean that it's still a constant? Yeah, 100%. As long as it's all by itself, it doesn't matter where it is in an equation. If it's all by itself, it's a constant. So in this case, 10 is our constant. 10 is the constant. It is a known number with no variables. Remember, a variable is a letter. So if it doesn't have any variables and it's a known number, it's a constant. Number 7, what are the coefficients, if any, to your answer to problem 4? So looking back at my vocab, I know that a coefficient is if one factor of a variable term is a known number, that number is the coefficient. So if I go back to my number 4 and I see a variable term, and that means that's a term that has a variable or letter. So over here, 4x, and then what's my coefficient there? So what's the number? So the coefficient is 4. And I know that because it's the factor next to x. So I think that actually being able to figure out, or like once you understand the vocab, doing this will be significantly easier. But understanding what coefficients are and constants and variable terms and terms is vital in understanding and how to do this. So this is just building up your foundational knowledge until we can actually get into the lesson. So it says, explain the difference between a constant and a coefficient. Well, that's pretty easy because a constant is a known number with no variables. There are no variables in a constant. Oops. But a coefficient is a little bit different because a coefficient is one known number and a variable. So that variable right there is the difference between a constant and a coefficient. And we are not done here. So it says use what you just learned about writing expressions to solve these problems. Show your work on a separate sheet of paper. So I'm going to go to the dry erase board for numbers 9, 10, and 11 and stay up there with you guys through this time. So number 9 says, write an expression with the same meaning as the result of multiplying 1/2 by a number, then subtracting 9. So on our dry erase board, we're going to go over here, and the first thing that I always like to figure out is what operation that they're using. In this case, they're telling me again, and I can see that that operation I'm going to use is subtraction because they say subtracting. That's my keyword. So I'm going to put that subtraction sign first, and then I got to think about my first and my second terms. And the first term looks like, see, instead of saying subtracting from a number, this one just says then subtracting 9. So in my head, whenever I see that subtraction, that's the first thing I'm thinking of is am I subtracting from this number, or am I going to subtract from my first number? So in my head, the way that my brain works, I'm going to think about that constant number, that 9, and I know it says then subtract 9. That's going to be my second term. That 9 is going to be my term. Whatever I do first, my second step is then subtract 9. So that's going to be my term 2. And then when I'm thinking about my result of multiplying 1/2 in a number, so they don't give me the number, so I know in my head I think of variables. So we're going to be writing down 1/2 times x minus 9. And that would be your final answer for number 9. The result of multiplying 1/2 by a number, 1/2 x, Then subtracting 9 minus 9. Beautiful. Looking at number 10. Write an expression with the same meaning as 7 less than the square of a number. Interesting. So again, I'm thinking of what operation are they asking me to do? And that operation, I'm seeing my keyword less than. So I'm thinking subtraction in my head. And then I'm trying to think of what are my two terms, my first term and my second term. 7 less than the square of a number. So 7 less than. In my brain, that makes me think when I square that number, I want 7 less. So I'm going to put that 7, that constant, as my second term. And now I got to think of 7 less than, so after subtracting 7, the square of a number. The square, that number they don't give me, so I know that I need a variable or a letter. And I know I can write x, and to square a number would be to write that 2 as a subscript. So write the expression with the same meaning as 7 less than the square of a number. Your final answer is x squared minus 7. And moving on to number 11. Write an expression to represent the sum of 3 and the quotient of a number divided by 6. So first things first, what operation am I using? Sum is my keyword. I know that that's addition. So I'm going to throw my addition sign up there, and I'm going to think about what are my terms that I'm looking for. In this case, I know that my constant, the sum of 3, so 3 is going to be my first number. Remember, in addition, does it matter what order that these two numbers come in? It doesn't matter in the addition and the multiplication aspect. But it is pretty important in the subtraction and the division. So you always need to be aware of the order that you're supposed to be in. So let's do the sum of 3 and the quotient of a number divided by 6. Quotient is the answer to a division problem. I know that a number, whenever I see the word a number, I think x or a variable of some sort. So I know I'm going to put my final answer of the sum of 3 and the quotient of a number divided by 6 as 3 plus x over 6. Because when I show x over 6, that is the quotient, the answer of a number, x, divided by 6. So now moving on to our next example problem. And this one says, read the problem below, then explore the ways to write and evaluate expressions with variables. So we're going to get a little bit more difficult here. Jennifer buys 1 pack of orange sugarless gum and 3 packs of mint sugarless gum. The pack of orange gum has 8 pieces. The packs of mint gum each have the same number of pieces. So the first thing that we're going to be doing is writing the expression that shows the number of pieces of gum that she buys altogether. And then we're going to figure out if each one of those mint gums has 6 pieces, well, how much gum does she have altogether? So the first thing that they ask us to do, or the first thing that they do for us, is that we actually get to picture it. So we can see, or you guys can draw this out. And this is a great first step if you're looking at something like this on a test. A great thing for you to do is to draw out what you know. And then by using this picture, it makes it easier to come up with things like your equation or your expression or answering a question. So here I can see my 4 packs of gum. Clearly I see my orange pack with 8 pieces, and I can see that I have 1, 2, 3 mint packs, and they each have p pieces each. We've been using x, but reminder that a variable can be any letter. In this case, they did p pieces. So the modeling it and coming up with the operation and your terms is the way that I like to do it and the way that I think that is very helpful. So let's look at how they show us at the bottom of this page. It says you can write a sentence describing the total number of gum pieces. And they did this by looking back at what they know. And they wrote the total number of pieces of gum is the sum, so the addition, of the number of pieces in one pack of orange gum and the number of pieces in 3 packs of mint gum. So again, always thinking about what operation am I using? That word sum in, the word sum in the sentence right here, the sum and the total number really tells us that we're going to have addition. So we put our addition problem, and now we have to think about what's our first term, what's our second term. And we're going to be doing that through this connect it. So reminder, I can't show you 2 pages at once, so you're really going to be needing to look at page 102 in your book as we're answering these connect it problems. Write an expression for the number of pieces in 1 pack of orange gum. So this is probably a little confusing. You're like, okay, I know that there's 8 pieces of gum in that orange pack. How can I write an expression? Ready, done. All you need to do is write down the number 8. How many pieces are in 1 pack of orange gum? 8. Very easy. Write an expression for the number of pieces in 3 packs of mint gum. So if you're looking back on page 102, I have 3 packs of mint gum and each pack has P pieces. So I'm going to write down the term for this as 3 times P, because I know that each pack has P pieces and I have 3 packs. So if I multiplied 3 by a number of pieces in each pack, I would get the total amount. So now I'm going to put those 2 together. These are my 2 terms. And it says write an expression for the sum of the number of pieces in 1 pack of orange gum and the number of pieces in 3 packs of mint gum. So the sum, first thing, I know addition. And my first term is the number of pieces in 1 pack of orange gum. Well, the number of pieces in 1 pack of orange gum is 8. So we're going to put that as our first term. Our second term says the number of pieces in 3 packs of mint gum. Well, we already came up with that expression too, 3P. So the expression for the sum of number of pieces in 1 pack of orange gum and the number of pieces in 3 packs of mint gum is 8 plus 3P. And then it explains how we can use the expression to find the total number if Jennifer has 6 pieces in each mint. So all we would have to do in this case is plug in 6 for P. So if I were to plug that in, I have 8 plus 3 times 6. And if I were to do that math, remembering of order of operations, we are going to be doing 6 times 3 first, because multiplication comes before addition in our order of operations. So we can rewrite this expression as 8 plus the product of 6 times 3, which is 18. And then we can come up with our final answer of 8 plus 18, and she will have 26 pieces of gum altogether. And now we're going to get to our try-its, which is I will be doing on the dry erase board with you. So Martina is 3 inches tall, 3 inches less than twice as tall as her little brother. Write an expression for Martina's height. How tall is Martina if her little brother is 28 inches tall? So let's start by figuring out what operation am I going to be doing in this problem. Martina is 3 inches less than twice as tall as her little brother. So less than are my keywords. And I am going to know that that operation is subtraction. So I'll put my subtraction symbol down. And now I'm trying to think about what are my two terms. So it says Martina is 3 inches less than twice as tall as her little brother. So when I'm seeing that subtraction where she is less than, and then my inclination or what I'm thinking is that I need to come up with an answer, and then I'm going to, at the end, subtract 3 more inches from it. So that makes me think in my head that my second term is that 3. Because when I double her height for as tall as her little brother, and then I subtract 3. So figuring that out in your head and before you write it down is super important. Just making sure that that order is crucial. So my second term is 3. My first term I have to think of twice as tall as her little brother. So remember, when I'm coming up with the expression, they didn't tell me how tall her little brother was. So that in my head, that's going to be my variable. I have no idea how tall her little brother is. If you don't, we're going to inevitably figure it out for 28 inches, but right now I don't. But I know that Martina is double her brother's height, so twice as tall is 2x. So my expression is going to be 2x minus 3. And now if I wanted to figure out how tall Martina was if her little brother was 28 inches tall, I am going to plug in 28 for x. So 2 times 28 minus 3. 2 times 28 is 56 minus 3. So our final answer for Martina is she is 53 inches tall if her little brother is 28 inches tall. And moving on to number 17. Tracy wants to remodel her bedroom with new carpet. She knows her bedroom is a square with walls that are 15 feet long. Use the formula as A equals S squared with S equal 15 to find the area of Tracy's bedroom. So remember, the S is standing for sides. And I think that it's very important to draw, just for you to see. We have this square. We know that each wall is 15 feet wide. And we're using the formula A equals S squared, and S is sides. But I also want to make sure that you remember that S squared is going to be S times S. So essentially we're going to be doing 15, A equals 15 times 15. And our final answer for 15 times 15 is 225 feet. And remember, this squared is absolutely important. So if we square 15, we're multiplying 15 times 15. And that will give us our 225 feet squared. Now moving on to number 18. Brian says that the expression 8n plus 2 is equal to 83 when n equals 1. Explain why Brian's answer is incorrect. So it seems like Brian, instead of plugging it in for a multiplication problem, so when we're plugging in our variables, we're plugging in a number for that variable, it's super important that we remember that we're multiplying. In this case, Brian, he just plugged in the 1 for the n. So instead of his problem being 8 times 1 plus 2 to give him a final answer of 10. Brian did 8, and he just plugged in his number 1, so he has 81 plus 2, and that's how he got his final answer of 83. So it's super, super, super important that we remember that this number, that when we plug it in a number for a variable, it is multiplying. And we're not just throwing it in there, because even if you just wrote it like this and came back to it and was like, oh, it's 81. And even though deep down in your soul, you know that you need to multiply, but you wrote it down wrong, it's not going to be helpful. So just making sure that you remember that this is the good way. We are multiplying. We are adding that number in, and we are going to be multiplying it by the coefficient. Okay? And moving on. Last modeled example this has been a long video before you guys get into your independent practice. So last year, the Speedster Bicycle Company held a bicycle design contest and awarded a cash prize. This year, the contest prize is $20 less than 3 times last year's prize. Evan and Gina win this year's contest and split the prize money evenly between them. So after we finish this example, we're going to write the expression to show how much prize money that Evan wins. And then if we know the variable is 50, how can we find that answer? So the first step that they did was to picture it, which is super important. You read it, you draw it out to what makes sense to you, because a lot of times reading those words doesn't quite put the math. When we see it drawn as a diagram, it really helps us, put that connection between the diagram, the words, and the math. So drawing it out is extremely important. And here I can see that they drew it out. They drew out the prize money as envelopes. So I really want to make sure that we go into a little bit of depth here, so that way the rest of the problem makes sense. This right here, this envelope, is last year's prize money. We have no idea in the beginning how much last year's prize money was, but we do know that this year's prize money is $20 less than 3 times that prize money. So I can see that they took last year's prize money, which is 1 envelope, they tripled it. So they drew it as 1, 2, 3 times. So last year's prize money times 3. And then they subtracted $20 at the end. And that's the overall prize money. But then they won it together, Evan and Gina. So they have to split that money directly in half. So first, let's see how the book models it. And remembering the contest prize is $20 less than 3 times last year's prize. The first thing that you need to think of is, what operation are they asking me to do? And they say $20 less than. I'm thinking less than always is subtraction. So I'm going to draw my subtraction symbol and then figure out my 2 terms. So that's our shape. First amount, subtraction sign, second amount. We don't know the amounts yet. And then there's a second part of this. We know that we have our shape of term minus term, but then there's the second part, that is that Evan gets half of this year's prize because he's splitting it with Gina. So we also have to take all of those numbers, the first term minus the second term, and you have to put that all over 2. Because when we finally figure out how much the prize is for the year, we're going to have to divide it by 2, because Gina gets half and Evan gets the other half. So let's look back into our connected. Reminder, you should have your remote learning book in front of you. You should be looking back onto that page prior, because I can't show you 2 pages at once. So making sure you're looking at page 104 while we are doing page 105. So it says, look at the model it on the previous page. This year's prize is $20 less than another amount. Will $20 be the first amount or the second amount? And then explain. $20 less than. So it's going to be the second amount. And I know that because I'm subtracting 20 from the product of 3 times x. So I know that that's going to come second. Explain how to write an expression for 3 times last year's price. So if I think of x, that variable, because I don't know the amount, the number of last year's prize. I don't know. So I have to think of last year's prize as x. So if I'm going to try to write this out so you guys can. Last year's prize is x. So this year, if they're asking me for 3 times last year's prize, I would be 3 times x, 3x. Write an expression for $20 less than 3 times last year's price. So using what we know from numbers 19 and 20 and what we know from using our picture it and our model it from page 104, I know, and especially, and this is very helpful, that 20 is going to be my second amount, and 3x is going to be my first amount. So I have 3x minus 20 would be my final expression for $20 less than 3 times last year's prize. And it says Chandler writes the expression 1/2 times 3x minus 20 to represent Evan's winnings. Is she right? Yes. She is 100% right. Woo! Because multiplying something, oh gosh, trying to type fast. Multiplying something by 1/2, oops, is the same as dividing it by 2. So she wrote it as this in the parentheses and then and then dividing the entire parenthesis. So yes, this is the same as multiplying an entire parenthesis divided by half is the same as dividing the entire parenthesis by 2. Explain how you can find how much money Evan wins if last year's prize was $50. So we need to plug, 50 for x. So I've got 3 times 50 minus 20 divided by 2. So I need to think in my head of order of operations. And so that first thing I'm going to be doing is this multiplication or these parentheses, and 3 times 50 is 150. So you guys can see I went down to, it's over here. So 150 minus 20, and then the whole thing is divided by 2. It's kind of hard to write this because looking at it on my screen, it looks like my next step would be doing 20 divided by 2, because when I think of order of operations, I think multiplication and division before I think of addition and subtraction. But because this is a drawback of being digital, I need you to think of this divided by 2 as being underneath, like if I did divided by 2. Like, I need you to think of it as being under it rather than next to it, because in this case, my next step is to do 150 minus 120, which is 130, and then I'm still have that division by 2. Again, this is a pain. I'm sorry if you're following along and being like, what the heck is she doing? I probably should have just drew this on the board. 150 minus 20 is 130, and then we're still over 2, and 130 divided by 2 is 65. So we've got $65 Evan is going to win. And then for numbers 24, I'm going to go to the board. So hopefully this might be a little bit more helpful. So let's look. The piece of 1 share of XYZ's stock drops by 2 cents. If you look at that, I can say that as 2/100ths, or as, because I see that dollar sign, I can think of it as cents. So 2 cents on Monday. On Tuesday, the price goes back up by 5 cents. Write an expression with 3 terms to show the change in price of XYZ stock. So the key word here is using 3 terms. So I need to think of, what do I not know? What is the variable here, and what operations am I using? So the price of 1 share of their stock drops by 2 cents. So I don't know how much their stock is originally worth, so that's going to give me my variable. So I'm going to use X. So X is going to be the original stock. And then when I think of my original X, it's saying it drops by 2 cents. So when I think of dropping, I think of subtraction. So it's losing 2 cents. So I'm taking away 2 cents. And then the next day it goes back up. So I'm adding that 5 cents in. So my final expression for 24 would be X minus 2/100ths plus 5/100ths. And then for the second part, it says if 1 share of the stock costs $34.18 at the start of the business on Monday morning, what is the price of 1 share stock by the close of the business on Tuesday evening? So they're basically saying it went through the drop of 2 cents, and then it also went back through the addition of that 5 cents. So our X, our variable, they're giving us a number here. So X equals $34.18. I'm going to plug that into my equation. So $34.18 minus 2 cents plus 5 cents. Whenever we are adding and subtracting decimals, lining them up is so incredibly important. So let's do 34 and 18/100ths minus 2/100ths. 8 minus 2 is 6. 1 minus 0 is 1. Decimals, and 34 minus 0 is 34. So after that initial 2-cent drop on Monday, we have $34.16. But now I need to go ahead and add back on my 5 cents. So I do 6 plus 5, and I get 11. I'll carry my 1. 1 plus 1 plus 0 is 2. I've got my decimal, and my 34 is being added on to nothing, so it stays the same. So at the end of Tuesday evening, your share will be worth $34.21. So now that we've completed the guided lesson, and I know this one was a little bit longer, but it does have a lot of great foundational skills that are required to be successful during the unit. I'm going to do the guided practice on the board. The 3 example problems are going to be up on the board. And then you are going to go ahead and complete your independent work. So the example right here, I'm not going to go over. If you are stuck in any way, shape, or form, this is an awesome example to go through, but we're already over an hour on this video, and I'm kind of trying to wrap it up. So let's look at these examples. Number 25. Georgia is 2 years younger than 1/3 of her Aunt Micah's age. Write an expression that describes Georgia's age. How old is Georgia if her Aunt Micah is 27? So when I'm looking at Georgia, I'm first trying to figure out what is the operation that I'm going to be using. So I see that she is 2 years younger than 1/3. So when I'm thinking of younger, she is less than her. I mean, just in terms of age, she's less than. So I am thinking of subtraction. And I know that I'm going to have 2 terms here, and I got to figure those 2 terms out. So Georgia is 2 years younger, 2 years less than 1/3 of her Aunt Micah's age. The variable that I don't know is how old is Aunt Micah? So to figure that out, Georgia is 2 years younger than, or 2 years less than. I know that's going to be my second term. So I'm going to put my 2 as my second term. My first term is going to be 1/3 of her Aunt Micah's age. And I don't know my Aunt Micah's age. So that number, I don't know. So that's going to be a variable. So it's going to be 1/3 x minus 2. And very quickly, whenever you see a fraction that has a numerator of 1 next to a variable, which is a letter, you can rewrite that as the variable x over the denominator 3 and kind of eliminate that 1, and then we can do x over 3 minus 2. So the second part says, how old is Georgia if her Aunt Micah is 27? So for that, I have to plug in 27 for x. So I'm going to put my 27 as x. So it'll be 27 over 3 minus 2. So the first step, thinking about order of operation PEMDAS, is that division. 27 divided by 3 is 9. I'm going to rewrite that. So now I have 9 minus 2. So I know that Georgia is 7 years old when her Aunt Micah is 27. So let's look at number 26. Shane is using pieces of square paper to cover a cube-shaped gift with sides that are 9 inches long. To find out the area of the paper he needs, he uses the formula for surface area of a cube, which is the area is 6 times the sides squared. What is the surface area of the cube? So in this case, we don't have to figure out a formula because they already gave us a formula. So we have to just plug in a number for S. S is our side length. In this case, each side is 9 inches long. So I'm going to write this as 6 times 9 squared. Because I'm plugging in my S. I'm plugging in 9 for S. And if you notice, the S is the number that's being squared. So I'm going to keep that squared with my 9. And I'm going to move on. My first step is doing what's inside my parentheses, 9 squared. When I'm thinking of that squared, I think of that's the number of times that my base number is being multiplied. So I'm multiplying the number 9 2 times. So 9 times 9 is 81. And it's always really important whenever you are solving for expressions and plugging in numbers that you stay very in line and you're rewriting your expression every single time that you make a change. If you don't rewrite it and you try to do it all on one line, then you'll forget things or you'll do things twice. It's just very important. So now I've got 6 times 81. So I'm going to do 81 times 6. 6 times 1 is 6. 6 times 8 is 48. So I know that the surface area is 486 square inches. For number 27, this one has multiple choice. Christy alters a skirt. She cuts 7 inches off the bottom and then adds a 5-inch ruffle to the skirt's remaining bottom edge. Which expression best represents the final length of the skirt? This one's a little bit interesting because when I'm looking at my options, I see A is 2 minus S, 2 plus S, S minus 2, or S minus 12. So what I first noticed before I even dive into this problem is I don't see any of the numbers that I saw in the problem itself. When I look into the problem, I see numbers like 7 and 5, but I don't see those in my answers. So let's try to figure that out. What I need to do here is figure out what operations I'm using and go from there. So Christy alters a skirt. Do I know how long the skirt was to begin with? No, the answer is no. I don't know how long the skirt was. So I can figure out that that is my variable because it's an unknown number. So I'm going to start off with X. I know that she's got this skirt and we don't have any idea what the starting length is, but she cuts off 7 inches of the bottom of the skirt. If I were to cut something off, I would be taking it away. So I'm going to subtract 7. If I were to just cut off 7 inches, it'd be gone. And then she adds, which is a key word using the exact symbol that we need, so bright addition symbol, 5-inch ruffle to the skirt's remaining bottom edge. So she adds 5. Which expression best represents the final length of the skirt? So when I'm looking at the problem that I have up here on the board, it says x minus 7 plus 5. These two, the 7 and the 5, are both constants. So when I see 2 constants, I can put those 2 together and make them into 1 constant. But this minus means that this is a negative. So negative 7 plus 5. So if I had negative 7 and I added 5 to it, I would go all the way up to minus 2. So I can rewrite this expression, x minus 7 plus 5, as x minus 2, and I could still get the same answer. So the correct response on your paper is letter C, S. They used S, sorry, I used X. So S minus 2. Evan chose D as the correct answer. How did he get that answer? So it seems like Evan got S minus 12 as his final answer. And when I'm kind of digging into this, I can see that it seems like he got the right original expression. He came up with x minus 7 plus 5. However, when he simplified it, he neglected or he forgot the negative in front of the 7. So basically, what Evan did was he left x minus and he just did 7 plus 5. And when you add 7 plus 5, you get 12. So that's how Evan came up with answer D, S minus 12. Because he forgot about this little symbol right here, that negative. So now I'm going to leave you off to do this independent work, the independent practice. There are, it looks like 6 questions, and a lot of them require showing your work. So please make sure that if you're turning this in on the Google Classroom, that you are showing your work still. If you're emailing or Snapchatting to me after doing it handwritten on your paper, that's beautiful. Just make sure that you show all your work. Just by giving me an answer, it doesn't really help me help you. So make sure that I can see how you're coming up with these answers so that if you do get it incorrect, I can come back and correct it accordingly. So I hope you guys have a great week. I know that this was a very long introduction lesson, but I think that it's well worth it to, especially making sure that you check out this video, and it will be very beneficial. So I hope that you guys all have a great rest of your week, and I will see you tomorrow.